So the half-life of first-order reactions. So the first-order rate law is when your rate is equal to K times the concentration of your reactant. We looked at the integrated rate law for a first-order reaction. We plotted the natural log of our concentration versus time. When that results in a straight line, we know that it's first order. When we studied the dinitrogen pentaoxide reaction, we found that the constant was 6.93 times 10 to the minus third per second. Our data looks something like this. So we have concentration over time. Notice that we started with a 0.1 mole per liter at time 0, and then we had half of it after 100 seconds. Then, as we proceed, we get half of the 0.05 after another 100 seconds. Notice that this trend continues for all of our data. What we want to do is be able to calculate half-life without having a list of data by knowing the rate constant. So a half-life of a first-order reaction is the time required for a reactant to reach half its original concentration. We'll call it T1/2 when we're looking at that specific time. So there's our data again. Notice that it always takes 100 seconds for our concentration to be halved. If we plotted this graph, we would see that here's our original concentration at time 0, and then it is half that amount at time, there's our little dot, 100. So after 100 seconds, we have half of the concentration. After another 100 seconds, we have half of the 0.05. So there's our current concentration at time 200. The next half-life occurs when you have half of the 0.025 moles per liter, and that occurs after another 100 seconds. So you always have a nice curve when you're looking at a half-life. This is concentration versus time. So our general formula, and I would like to derive this with you, and then you'll see where it is on your AP sheet. And this is just for a first-order reaction. We have a reactant giving us a product, and we know the integrated rate law gives us the natural log equals negative rate constant times time plus the natural log of our original concentration. So the first thing I'd like to do is move our KT to the other side. So I'm going to have plus KT, don't really need the plus, and then I'm going to take my natural log of the original concentration and subtract the natural log of my concentration. You might remember when you subtract natural logs, you actually divide the two. So I have KT is equal to the natural log. In the numerator, we have the original concentration, and in the denominator, I have the current concentration at time t. So let's keep working with this. We're trying to find, how do we find the half-life, the time for the half-life? So our next step, if it's half-life, we want the concentration to be half the original concentration. So half the original can be original concentration divided by 2. So looking at the equation you just had, I'm going to take K, and now I'm going to make T have a subscript of 1/2. My natural log, in the numerator, I have A naught, which is our original, and then A, I'm going to substitute in half the original concentration, because now we are very specific about wanting the time for the half-life, right? So let's think about what's in the parentheses for a moment. So I have K, T1/2 is equal to natural log. So we just have A naught divided by A naught divided by 2. So I'm going to take my lower fraction and invert and multiply. So you can see that the original concentration does not have anything to do with it. And so I now have the constant multiplied by the half-life, natural log of 2. So my t1/2 is equal to the natural log of 2 divided by k. Let's take it one step further. Since natural log of 2 is a constant number, we can calculate that, and it's 0.693. K is our rate constant for a first order reaction, and t1/2. So this does only apply to a first order. And if you look at your AP equation sheet, it's right down there at the bottom. You just need to know how to apply this equation. So our next little exercise is to determine the rate constant for a first order reaction with a half-life of 20 minutes. I'm just going to leave the time in 20 minutes. So t1/2 is 20.0 minutes. We want the rate constant, so we're finding K. And we know that our new equation is t1/2 equals 0.693 divided by your rate constant. So K is 0.693 divided by 20 minutes. And once you do your math, you have a value, and I'm just going to keep it in minutes again, 0.0347 per minute. All right, because the minute unit is in the denominator. So now you know your K value. Our last part of the problem asks, how much time does it take for this reaction to be 75% complete? So this one takes a little bit more thought. So if it's 75% complete, we know we have 25% left. Because think, if we started with 1, after one half-life, we're going to have 0.5, and after another half-life, we have 0.25. So it's 75% complete. So we know that the ratio of A to A naught is 25%, or 0.25. Okay, I want you to start there. Now think about our basic equation is the natural log of A is equal to negative KT plus the natural log of your original concentration. Oops. So you should look at your AP sheet and just get used to what it looks like. They write it a little bit differently. We are solving for T, so I'm going to bring KT over to the left again, as I did previously, and we have the natural log of A naught over A. Now, notice when I was thinking about this problem, I have A over A naught for concentrations. And inside my natural log, I have the inverse. So to take the inverse, because I want the original over the current, if I have 1 over 0.25, that's going to give me a value of 4. So my time, I'm going to do a couple of steps here. I'm going to have the natural log of 4. Okay, again, I got that just up here, divided by K. This is the same problem that we just calculated the K for. So we have the natural log of 4 divided by 0.0347 per minute. Let me rewrite that. And do your math, and you're going to get a value, once rounded to 3 sig figs, of 40 minutes. So the time for this reaction to be 75% complete will take 40 minutes.